Okay, so we covered some sampling distribution stuff where we said if you have a population with a certain proportion this and you take a random sample, we know the sampling distribution comes from a normal model with these properties, this mean and this standard deviation. Now, there are some conditions that must be true in order to use the normal distribution as an approximation. Okay, so to use, to use the normal model as an approximation, for the sampling distribution, a few conditions must be met. Okay, so if these conditions are not met, the thing that we just learned about using the normal model and normal distribution does not apply. It no longer works. Okay, so there are three conditions that must be met. Otherwise, you cannot use the normal distribution. Okay, you can't apply the things that we just learned. I'm going to sit down. My back it hurts being hunched over. Okay, so if these conditions are not met, cannot apply normal distribution. Okay, so this is also known as conditions for using the central limit theorem. Okay, and the central limit theorem is basically just a fancy way of saying, hey, we can use the normal model to approximate the sampling distribution. Okay. Where did my pen go? Okay. So I mean, it's a little more complicated than this, but for the purposes of this class, we're just going to say the central limit theorem is a fancy way of saying that we can use the normal distribution to approximate a sampling distribution. Actually, slide over completely over here. Oh dear. Okay, all right, so the three conditions. Three conditions that must be met okay. One, the random and independent condition. Okay, so this means the random independent condition says that the sample must be drawn randomly and the individuals must be selected independently. Okay. So somewhere in the problem, it should state that the sample was selected randomly. This is a little risky. Okay, condition number 2. Okay, this, and I can't remember the order that the book puts these in. Let me just check to make sure I get the same order as the book. The large sample condition, okay? Okay, and this basically says our sample must be large enough. Okay, now how do we know what is large enough? Okay, 2 things. So the large sample condition, there's actually 2 parts to the large sample condition. Okay, and these are the 2 parts. N times P has to be greater than or equal to 10, and N times 1 minus P also has to be greater than or equal to 10. Okay? Or another way of saying this is if you don't have N and P, there must be, so let me just wait, another way of saying this. Okay? There must be at least at least 10 successes and 10 failures. Okay. Now the labels success and failure are arbitrary, so let me just slide this up here. Okay. Oops. And lastly, we have the big population condition. So normally I'm facing the chalkboard, and I don't notice all of you guys falling asleep, but I can see you guys do it, all right? All right. So I know, it's statistics. I try to make this as engaging as I can, but sometimes there's only so much you can do. All right, the big population condition. This says our population must be at least 10 times bigger than our sample. Okay, so if our sample is size 50. If we're taking samples of 50 M&Ms out of the tub, there must be at least how many M&Ms in the tub? At least 500, okay? And let's say if there's 1,000 M&Ms in the tub, what's the biggest sample I'm allowed to take? 100, right? I cannot, so our population has to be at least 10 times bigger than the sample, okay? All right, so let's save that. And here, let me copy this. Our 3 conditions here. And let's try a problem here. Okay. Let me shrink this. Okay, so, all right, so we'll try example problem. Example problems. Okay, so we're going to say, I'm going to write a scenario out, and you tell me if any of these conditions have been violated, okay? Now, don't shout out your answer, because some people will take a little bit longer, and we just want to give everybody a chance to think through this. Okay, so don't shout out your answer, but I want you to tell me if any of these conditions are violated. Okay, so you decide to take a survey at school. Okay, you select 5 classrooms at random and survey everyone in those classrooms. Okay, you surveyed a total of 180 students. Okay, there are 6,000 students attending the school. Okay, and then 32% of students surveyed I don't know, do not own a toaster. Okay, so read through this. Tell me, are any of these conditions violated? Are they all met? What's going on here? So think through that. Are we still copying? Do we have an answer in mind? Yeah? No? Okay. Are any conditions violated? Yes or no? Yes. Which one is violated? The random and independent condition. Random and independent condition. All right. Why is that one violated?
They're not independent of each other, they're all the same classroom.
Random and independent condition violated. Okay. It says we selected 5 classrooms at random, but you're surveying everyone in those classrooms, okay? So these students are not selected individually one at a time, okay? Students are not selected independently from each other. Okay? Everyone is selected together, okay? All the students are selected together in the classroom. So that condition is violated. This would actually be a form of cluster sampling, but that's not what we're going for here. Okay. If we were to check the other ones, large sample condition, is that met? Yes, okay. We can check the large sample condition, and this is met. Because we would do n times p, which would be what? 180 times, what's p? 0.32, okay? And I would do n times 1 minus p. So I would have 180 times 1 minus 0.32, okay? And so I can check both of these things. 180 times 0.32, whoops. I get 57.6. And I do 180 times 1 minus 0.32. I put that in parentheses. Okay, and I get 122.4. Okay, 57.6 is bigger than or equal to 10, and 122.4 is also bigger than or equal to 10. So large sample condition is met. Okay, and then the last one, big population, is that met? How big is our population? Population is 6,000 students, and our sample is 180. 180 times 10 is 1,800, and that's less than our population. Okay? So big population is met. Okay.
Just the second one?
So just the random and independent condition was violated. Okay? Sample must be drawn randomly and the individuals must be selected independently. Okay? So it should be saying that the sample is selected randomly. This one, it says that the classrooms were selected at random, but everybody was selected in the classroom, so that's not independently. Okay? Is that good?
How could you modify this so it works?
Okay. You could say, so if we wanted to make this work, I would scribble out this line. And I would say you select a total of 180 students at random from the school. Okay? So if I said you decided to take the survey at school, you surveyed a total of 180 students at random from the school, and then there's 6,000 students attending the school. 32% of the students surveyed do not own a toaster or whatever we're looking at. Okay? Then in that case, the random and independent condition is met because you're selecting these 180 students at random. Okay, so is the difference there okay? Okay. So I'll say, don't say that. I actually go back. Let me select this again. So this is kind of a nice little feature. And I can't do this with a chalkboard. Okay, let's try another thing. So another example problem, and okay, so I guess this is your fair warning. on the quiz next week, you will see a few problems like this, okay? I'm going to list off scenarios just like this. Of course, not exactly like this, but a little bit different. And then I'm going to ask, are any conditions violated in this scenario, or are they all met, or whatever? And you have to tell me which one's violated, okay? So let's try another one. Okay, so you decide. Let me. You decide to check the inventory of, I don't know, of shoes in the back room at Foot Locker. All right. What's going on here? Okay. All right. There are a total, I have no idea how many pairs a store might have. There are a total of 800 pairs of shoes, or we'll say 800 boxes of shoes. Boxes of shoes in the store. Okay, not story. You check 60 boxes and find that 5 of the boxes contain shoes with some kind of defect. Defect or, I don't know, scar, stain, or I don't know, where. Okay. Are any conditions violated to use? So don't shout it out, but think about this. Oh, I'm sorry. You check 60 boxes randomly. Actually, I'll say that, randomly. And find that 5 of the boxes contain shoes with some kind of defect or wear. Okay, what do you guys think? Violation, no violation?
Violation.
Violation, what's violated? Number 2, large sample condition. Okay, so let's go through each of these. Okay, random and independent. Is that met? Random and independent is met because it says 60 boxes at random, okay, or 60 boxes selected randomly, okay? Large sample condition is violated. Okay, what do we have? We need to have 10 successes and 10 failures. And what do we have? We have 5 with defects or wear. And so that means how many do not have defects or wear? 55, right? We have a total of 60 boxes. So 55 with no defects. Okay, but 5, is 5 greater than 10? Okay, it's not. Not greater than or equal to 10. Okay, 55 is, but 5 is not. Okay, so because of this, our large sample condition is violated. What about big population? Is that okay? And why is that one okay? Yeah, because we have a total of 800 boxes, and we looked at 60 of them, okay? So our sample is 60, and our population is 800, okay? So 60 times 10 is 600, which is less than the population. Okay? We just need to make sure that our population is at least 10 times bigger than our sample. Is that good? Okay. So if you see questions like this on the quiz next week, we'll be okay? Okay, good. Because you will. All right. Okay. So in your notes, you should have starred the M&M problem from the VAT. Okay, you're not going to get an M&M problem, but something similar to that, where you have a population. We're taking random samples from the population. I'm asking, well, what's the probability that your sample looks like this? And then you should also have starred these two examples here, where you are given scenarios and you have to identify which condition is violated. Okay, so we have another thing to learn, and this is confidence intervals. Okay? All right. And confidence intervals, this is specifically confidence intervals for P based on a single sample. What was P again? P is the proportion in the population okay? Or sometimes it's called the population proportion. Okay? So this is the percentage of all Instagram users that are female, or the percentage of all the M&Ms in the tub that are green, or the percentage of whatever in the population that is P, okay? Now, with a confidence interval, the idea is, hey, wait a second, I don't know what the proportion in the population is, okay? So in the previous problems with the tub of M&Ms and the tub of Reese's Pieces candies, I said, hey, we happen to know that in the tub, 30% of the candies are orange. Or hey, we happen to know in the tub, 18% are green, okay? In this scenario, we're saying, I've got this giant tub, and I didn't bother counting all the things, so I don't know what percentage are green, or I don't know what percentage are yellow, or I don't know what percentage of users are female, okay? Because I didn't bother counting them all. But if I take a random sample, let's say I select 100 candies, 100 pieces of candy, and I count them out, let's say my 100 pieces of candy turn out to be 33% orange. What does that say about the proportion in the tub? Okay. Well, does that mean the proportion in the tub is exactly 33% orange? No. But it gives us an idea that the percentage in the tub should be something like 33%. Maybe it's more than 33% and we happen to get a sample with less than what's in the tub. Or maybe it's lower than 33% and we happen to get a sample that was more than what was in the tub. We don't know, okay? But if our sample of 100 candies is 33% orange, then that means what's in the tub should be something around 33%, okay? And the thing is if we took bigger samples, then the number we observe in our sample should be closer to the actual percentage in the tub, right? Whatever, if we take a huge sample, our sample proportion should be very close to the population proportion. If our sample is small, then we would expect there to be some kind of give or take, a little bit more leeway there, okay? And that's what a confidence interval is all about. We observe a sample, and based on the sample, we want to say something about the proportion in the population. And so we will see a formula. Okay, I'm going to put a formula up. But the important part is the idea behind a confidence interval. Okay? So the idea is, this is the idea. The big idea for confidence intervals. Okay? We do not know, the big idea is that we do not know P. Okay? We do not know the population proportion. Okay? Do I have to write we do not know the population proportion if I just write we do not know P? It's okay, right? Okay. We do not know P, but we take a sample and from the sample we observe what is the symbol we use for the sample proportion? P hat, okay? So we take a sample, and from the sample we observe P hat, okay? P hat is probably not exactly the same as P. Okay? But we expect P to be fairly close in value to P hat. Okay? So we're going to say, I'm fairly confident, let's say I take a sample of candies, 33% of my candies in this sample are yellow, okay? So based on, I took a sample of 100 pieces of candy, 33% of those are yellow, okay? And what I'm going to say now is, well, P, I'm pretty confident, is close to 33%. And I would say P is, 33%, give or take 6% or something. I'm making up a number here, okay? And so I say, I don't know exactly what P is, but I'm pretty confident that it's going to be 33%, give or take 6 percentage points. So it would be between what? 33 minus 6 percentage points would be 27%, and 33% plus 6 percentage points would be 39%. And so I'd say, well, I don't know what P is, but I'm pretty confident it's going to be between 27 and 39%. Okay? And that's all a confidence interval is. We look at a sample, and we're saying, based on what we see in the sample, what does this say about P, the proportion in the population? Okay? And we have formulas for that, but the big picture idea is we don't know what P is, and so we take a sample, and we see P hat, and based on that P hat, we're going to try to make basically an interval. P hat, give or take some value, and we're confident that P is in there. Is that concept okay? Okay? So I'm going to put some formulas and equations up here. Don't get distracted by those things. For some reason, students love these little formulas and things, and they're like, this is going to solve everything. No, the important part is the understanding and the interpretation of what we're doing. Okay? That's the key. The formula is important. is how we get the numbers that we use. So it is important, but just as important is the understanding and interpretation. Okay, so a confidence interval will basically be p hat plus or minus, and I'm going to write this thing called the margin of error. Okay, so this could be an example is I take a random sample of Reese's Pieces candies. %, of the sample is yellow. Okay, let's say the margin of error, and I'm going to abbreviate that, ME, okay, margin of error, ME, is 6%, okay? So my confidence interval is 33% plus or minus 6%, which basically is 33% minus 6% is 27%, to 33% plus 6%, which is 39%, okay? This is my confidence interval. Okay, now I'm going to have to explain how we calculate the margin of error, okay, which will be the next slide. Okay, but do we understand this concept that I'm going to say, you know, I take a random sample and I'm going to put that in the middle and I go plus or minus a margin of error. Okay, and if we might not deal with percentages, maybe equivalently I could just do 0.33 plus or minus 0.06, and that gives me 0.27 to 0.39, okay? So you have to be just as comfortable dealing with decimals as percentages, okay? But this is all the same. So I'll let you guys finish copying that. Wow, it's so different spacing out. I'm like tripping out here. Because normally I always have my back turned towards you guys because I'm writing up on the board. But now I can see all of your guys' faces. I can see something happening over in that corner over there, and I don't know what's going on, but whatever. Okay. Yeah, what's up? Yes.
So the 33% plus or minus 6% translates to the two below it, and then to the left, that's in decimal form.
Yeah, so over here I've got it in decimal form, and over here I have it in percentage form, okay? But it's the same thing, right? Here all you're doing is you're doing 33% minus 6 percentage points, 27%, okay? 33% plus 6 percentage points gives us 39%, okay? That's not a... We can do that, right? That's just arithmetic, okay? All right, so let me tell you how to calculate the margin of error, which is, I guess, the hard part of the math. It's not that hard, okay? All right, so confidence interval. Again, continued. Basically, it's going to be p hat plus or minus the margin of error, okay? And the margin of error is given by z star times the standard error, okay? Okay, and over here, the standard error, and this is the standard error and our formula for the confidence interval changes, but the standard error for p hat, okay, because we have one sample, is equal to the square root of p hat times 1 minus p hat over n. Okay, so I'm going to just plug this thing back into our formula, and we have p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Okay, and again, this part, this whole thing over here, this is known as the margin of error. Yes?
So the equation to the right is to find the standard error.
Yeah, this is just getting the standard error. Okay. Now the standard error equation, I hate to tell you this, but it's going to be different for each type of problem. So this week this is the standard error, and then next week we'll learn another type of problem, and the standard error is going to change, and so on and so forth. Okay? It's exciting. Right? It is. Okay. All right. Okay, so let's do, and let me talk about Z star, okay? So there's all sorts of, there's different ways here, and to talk about Z star, and I'm going to just default to the most basic explanation, which is I'm going to give you 4 numbers that you either have to memorize or make sure you put on your note card, okay? There's just 4 numbers that you need to know for Z star. You must know, okay? And so based on how much confidence you want to have will determine the Z star that you use, okay? So if you want to be 90, so I'm going to do the confidence level. And this corresponds to the Z star to use. Okay? So if you want to be 99% confident, the Z star you use is 2.58. If you want to be 95% confident, the Z star you use is 1.645. I'm so sorry, not 1 point. I messed that up. 1.96. 1.96, I apologize. Messing up here. For 90%, that's 1.645. And for 80%, use 1.28. Okay? So these are the 4 numbers you need to know. So either memorize these or make sure you put them down on your note card. Okay? Don't come crying to me next week and say, I forgot what the Z star values are. Okay? You must know these. Okay, so make sure you put these at least on your note card or memorize them, okay?
So, will the problems you give us always include a confidence level between 99% and 80%?
Yes, okay. And so, you know, technically you could make a 97% confidence interval and you would need a different Z star, or a 92% confidence interval and you need a Z star. But those are very uncommon, okay? It would be like, I don't know, just trying to get something weird. It's very uncommon. It's an odd, it's like asking the ATM to give you $33 in cash or something, you know? You just don't do that. All right, so let's try a problem here. Okay, so example problem. So you take a random sample of 200 Instagram users. All right. So somehow you got a random sample of Instagram users. Okay. Of your sample, okay, 132 are women. Okay. So make a 95% confidence interval for the proportion of women, or proportion of all Instagram users who are women. Okay. Do you guys want to try this out on your own, or you just wanted to do it? Okay, so go ahead and try this out then, okay? And let me